Hello everyone, my name is Eddie Britt and I'm going to work on your test 3 practice. It does say spring 2019 at the top, but I do use these tests more than one semester. Since all the numbers are randomly generated, I can do that. Usually for the practice test, I lock all the values and keep it in the same order. That way I can work one out for you and then you can go in and practice it if you need to. Alright, we're going to start here with number 1. It says classify the following as either a discrete random variable or a continuous random variable. Remember, discrete is countable. Continuous, I mean it could be every value in between any two sets of values. So the heartbeats per minute of 64 randomly selected people. 64 people, you can't have 64.5 people, so that's a countable number. So that's going to be discrete. Alright, this problem, which plan has the least amount of risk? For amount of risk, we need to figure out the standard deviation. And so this is going to be kind of a long problem, probably one of the longer ones on the test, because you can't just eyeball it and tell. Whenever I first looked at these two problems, or these two plans here, I said, well, you know, anyone would always want to invest in plan A because, look, it never loses money. I mean, it's always going to make money. And then this one here does lose money 9% of the time. And so we just have to, but we have to break down the statistics and show one way or the other, because sometimes, you know, what we think is not the actual answer as far as risk goes over a long amount of time. Now, one might make more money, but which one has the least amount of risk? And so the least amount of risk is going to be associated with the one that has the smaller standard deviation. So that's what we need to do. So we're going to need these values here to do that. In some cases on the test, I've already worked a lot of the values out. That way it won't take that much time for me to go through the problems. But this is kind of a longer problem, so I'm going to copy this over here. Alright, so again, I've got to find the standard deviation for both of these plans. And to find the standard deviation, you first need the expected value. And expected value is like the mean of the set of data. Now calculators will do that. I did all this out by hand, so I'm just going to show you what to do to find the expected value for each plan. Again, the expected value, that's going to be like the mean, that equals. So what you have to do is take and multiply these two numbers together, and then write that number out to the side. I have a little space right here, so that's what I'm going to do. So I'm going to pretend that I'm multiplying here, here, and here. And so for each one of these, I'll get a number. I have 5,500 when I multiply the first two. Multiply the second two, I have 8,400. And multiply the last two, and I get 42,750. Now when I add all those up, when I take the sum, that's going to give me the mean. Alright, and I've already done that. I get 56,650. And I'm going to do the same thing here for the other set. I'm going to go ahead and find the mean. So I need to multiply each one of those. So for the first one, I get negative 2,250. For the next one, I get 2,400. I didn't do a very good job of lining those up. And then the next one, I get 16,750. And that's when I multiply those two together. So again, I want to take the sum of all of those, and that will be my expected value, which is the mean. So when you add those three numbers together, you should get 16,900. Alright, so that's the mean of each set. Now, I'm going to need to figure out the standard deviation. And the way that we figure out the standard deviation is we have to say the x value, which is the payout, minus the mean, our expected value, squared, and then that times our probability. So times our p of x. So we're going to do that for each value and then sum those up. When you sum those up, that gives you the variance, and we'll take the square root of that. So we'll take the square root of all that, and that will give us the standard deviation. All right. So again, these calculations take a little while. I've already done all of these in my calculator. So you say 25,000 minus the mean, which was 56,650. We're going to square that and then say that times 0.22, right, because that's our probability. All right. This is what I got. I'm not going to talk as much as I write these others down, just so I can get them written down a little faster. And though I'm sure that you enjoy listening to my voice, hopefully you're not asleep by now. Wake up. So you see these numbers are really big, and some of these are in the hundreds of millions. Alright, so we want to take and find the sum. If you find the sum of those, that's your variance. Okay, so that's your v of x, your variance. I want the standard deviation. The standard deviation is the square root of that number. Okay, so I have standard deviation equal to 21,691, and I'm just going to carry it out to 3 places. So 0.646. Alright, I'm going to do the same thing for plan B. So I'm following this same formula up here. Alright, so I'm going to sum all these up. I'm going to sum them up. 235,041,300. So that again is my variance. So my standard deviation is the square root of my variance. And I get 15,331. If I round that to 3 places, that'll be 0.057. Alright, so if you have a larger standard deviation, of course that means greater variability in profits and in risk. So if you have a smaller standard deviation, then that would be less risk, less variability in your profits and less variability in your risk. And the problem asks us which has the least amount of risk. So that's going to be plan B, because you can see 15,000 something is less than 21,000 something. Now, which one would I choose? Like, if I was want to invest money and make more money, I'd probably choose plan A. But statistically, plan B has less risk, but less profit as well. So we have to go with B. All right. And again, that was one of the longer problems on the test. So let's see, problem number 3. Decide whether or not the distribution is discrete probability and select the reason why or why not. It's okay for my random variables to be negative, but I have to make sure that none of my probabilities are negative. That's okay. So none of them are negative. The other thing I need to check out is make sure that all of my probabilities add up to 1. So that'll be a probability distribution. So all I need to do is add these probabilities together and make sure that I get 1. All right. So I have 5/8, I had 1/8, and I had 1/4. So I just need to get a common denominator of 8. So 1/4 is 2/8. So that's 5 plus 1 is 6 plus 2 is 8. So that's 8 over 8, or 1. So yes, this is a discrete probability distribution. Yes. And why? All right. It is a discrete probability distribution. So probabilities lie inclusively between 0 and 1, and the sum of the probabilities is equal to 1. So we have to check for both of those. So I couldn't have a negative probability here. That's what that says. And I couldn't have a probability greater than 1 for one of these. Okay. All right, the binomial distribution. So to work this problem out, we don't have to figure these values out. They're already given to us. We just have to make sure that we plug them into our calculator correctly, or into the formula correctly, really. So, you know, the formula sheet, I should have given you all that by now. I know I have if you've taken your Proctor exam. This is chapter 7. So we're using this formula right here. This binomial probability distribution formula. Alright, so it is NCX times P to the X times 1 minus P to the X. Nope, not X, N minus X. Alright, so the problem gave us all the values. It told us that N was 9. It told us that X was 2. And it also told us that the probability is 0.1. Alright. The only thing it didn't tell us is what 1 minus P is, but we can figure that out. And we also have to remember to raise the 0.1 to the X power. So that's going to be to the second power. And then times 1 minus P is 1 minus 0.1. 1 minus 0.1 is 0.9. So it's going to be 0.9 to the N minus X power. So 9 minus 2 is 7th power. Alright. So what I would probably do is work this out first. Remember, you can use your calculator to do that, or you can say 9 factorial divided by, and then it's 9 minus 2, that's 7 factorial times 2 factorial. And so you work that part out, and then multiply that times 0.1 squared, and then multiply that times 0.9 to the 7th. And you should get 0.1721868884. I like to take mine out a lot of places. That way, depending on what the test wants, I can just put in that many. So it says to 4 decimal places, so I can type that in. That's going to be 0.172, and then I have to round the next digit, so it's 1/8, so I'm going to have to round that up to 2. Alright, again, it said to the 4th digit, that's right there. Look at the next one, round it up if it's 5 or greater. So alright, so this problem is talking about, let's see, mean flaws per 100 feet. What's the probability to be exactly 3 flaws? This is a Poisson problem, so we need to use the Poisson formula. Alright, so you see it right here. Here's the Poisson formula. We need e to the negative lambda times lambda to the x divided by x factorial. Important we use the correct formula, especially on one like this. So probability is going to be equal to e to the negative lambda times lambda to the x divided by x factorial. So what are our values? Let's see. Lambda, remember, is like our average value. So we have to figure out the average value. Alright, so it says it's a mean of 0.7 flaws per 100 feet. But we're looking at 1,400 feet. So 1,400 divided by 100 would be 14. So we have to say 14 times 0.7, and that will give us the average number of flaws per 1,400 feet. Again, it gives us 0.7 per 100, but this is 1,400. So 1,400 divided by 100 is 14. 14 times 0.7. So whatever 14 times 0.7 is, that is our average number of flaws. And I did that in a calculator, and I got that our average number of flaws is 9.8. Alright, and the problem asked, what's the probability that exactly 3 flaws will be in 1,400 feet of cable? Alright, so that means our x is 3. Alright, so we're going to say e to the negative, because the formula is negative lambda, so e to the negative 9.8 times 9.8 to the x power, so to the 3rd power, divided by 3 factorial. Now some of my students have an issue pushing all this in the calculator at once. So if you need to, type in e to the negative 9.8 first. So if you're using, even just the regular Windows calculator will do this. You can see there, if you have it in scientific mode, there's an e to the x button. So if I type in 9.8 and I make it negative, the way you raise it to the power in this calculator, you just push that. And you can see that it's a really small number because this is in scientific notation right now, and it's times 10 to the negative 5 power. So what I would probably do, especially if you're using a calculator that gives you an answer like this, is I would just leave that in there, and then I would say times, so you can see what we're putting in up here, and then I need to say 9.8 to the third. So parentheses 9.8 parentheses raised to, so that's the x to the y button, so this raised to the third power. And when I hit equals, it's going to give me what that is equal to, all that. Now it's divided by 3 factorial. 3 factorial is 3 times 2 times 1, so that's 6. So I just say divided by 6, and that's my answer. So I'm going to write this out to a couple digits, and then I'll round ever how it wants me to round. So that was 0.008698434. And it was actually 8433, but whenever I did it in my calculator, one of the scientific calculators, it stopped right there. Alright, so it wants us to put this answer in 4 decimals. That happens a lot. So let's put this in using 4 decimals. So that would be 0.0087. All right. This next problem, I can already tell, is a hypergeometric distribution. And so the hypergeometric distribution, again, you have to use the right formula. You can see it's a little more complex. Put this over here on my page so I don't mess it up. And of course, we have to know what each variable stands for. All right. So I'm going to need the problem. So it says 7 of the 23 patients have a heart problem that will result in death if they receive a test drug. 6 patients are randomly selected to start receiving the drug, and the rest receive a placebo. What is the probability that exactly 4 patients will die? All right. So the total number of patients is 23. 7 of those have a heart problem that will result in death if they take this drug. They choose 6. So the number of chosen, that's going to be the sample size. So that's little n. 23 is the big N. The number of successes, and I wouldn't consider it a success that someone died, but the number of successes here for our variable k is 7. And then exactly 4 patients will die, x equals 4. So I have to write all that down first. All right, so number of successes, possible successes with 7. The total number is of patients is 23. The sample that we're taking is 6, and we want to know the probability that exactly 4 die. All right, and so you see our formula up here. We're going to have 3 different combinations that we have to work out. So it's 7C4 times, you would say the total number of patients minus the number of successes. So that's going to be 16C and then the sample size minus the x. So 6 minus 4 is 2, divided by, and then I have the entire number of patients, so that's 23, C, 6. Okay? You can work out each one of these in your calculator, or work them out using the formula, but you're going to get 35 times 120 divided by 100,947. And when you do that, you're going to get 0.041605991. All right, and the problem, if it tells us to round to 4 places like all these others, we stop there, have a 0, so we do nothing. So 0.0416. And it does say 4 places. All right. So here, this looks like a uniform distribution problem. Polar bear frozen foods, manufacturers frozen French fries. The final weight, package weight, is thought to be uniformly distributed, be a uniformly distributed random variable. Assume X, the weight of the French fries, has a uniform distribution between 53 ounces and 59 ounces. What is the mean weight for the package? What is the standard deviation for the package? Round your answers to 4 decimals. Okay. So we have formulas for this uniform distribution. Okay, they're right here. For the mean, it's A plus B divided by 2. That's the 2 numbers it gave us, divided by 2. And for the standard deviation, it's B minus A divided by the square root of 12. So that's the 2 formulas I'm going to use. Alright, so it told us the weights were between 53 and 59. I think it was ounces, pounds. It really doesn't matter. So we'll just say 53 plus 59 divided by 2. Add those together and divide by 2, and you get 56. Alright, so that's the first answer. And then the formula for the mean was B minus A divided by the square root of 12. I could explain to you why that square root of 12 is there, but I would probably need to use some calculus to do so. So just take my word for it. There's a square root of 12 in the formula. All right, so that's going to be 59 minus 53 divided by the square root of 12. Do that in your calculator, and you should get 1.732050808. It said 4 decimal places, so there's the 4th decimal place. So it's going to be 1.7. No, I lied. The 2 is the 3rd. Yeah, that is right. So it's going to be 1.7321. All right, there's no decimal places here. If you want to put in 0.0000, I guess you can. I would think it should take it either way. I'll put the decimal places in so that we can see if it takes it that way or not whenever I submit my test at the end. If it tells me I got that one wrong, then I'd say don't put it in. We'll see. All right, so let's type those in. So the first one is 56. And the second one was 1.7321. This is another, this is a uniformly distributed problem, probability with uniform distribution. The way that I like to look at these is like part over total. There's another way you can do it, but I always try to work these problems the easiest way, unless that involves just using a calculator to do. So, this told us, this problem said that the tree is going to grow, or cedar trees will grow between 6 and 13 inches each year. Find the probability a randomly selected cedar tree will grow less than 8 inches in a given year. So one way to do that is by constructing a rectangle and letting the height of the rectangle be the probability and all that. The way that I do this, to me that makes the most sense, I think about the range of values that it gave us, like it's on a number line. It said it's going to grow between 6 and 13 inches. And the distance between 6 and 13, that's 7 units. Okay? 7 units between 6 and 13. That'd be 7 inches. And then it wanted to know what's the probability that it will grow less than 8 inches. So, remember, this 7 doesn't stand for the number of 7 on the number line. That's the distance between 6 and 13. Now, 8 would be somewhere, let's say 8's right here. If 13's here, 6 is here, 8's probably about right there. So what part of that is between 6 and 8? Well, that's 2 inches. Maybe I should put that in a different color. So that's 2 inches there. So if you just do 2 over 7, that's your probability. 2 over 7. Part over total. To me, that's, since it's uniform, you can do it that way. It says around the 4 decimal places, so I'm going to say 2 divided by 7. So 0.2857. All right. The diagram below is an illustration of the empirical rule. So if you don't remember the empirical rule, you might want to look back at that. That was maybe like around the 3rd or 4th chapter. Select a missing label for the diagram with a list of choices. So the total area under this curve is 1. The shaded region here is 0.6826, it tells us. That's about 68%. And the 1 sigma rule said that about 68% of the data items are going to lie within 1 standard deviation of the mean. The mean is right here in the middle. Okay? If you go 1 standard deviation to the left, that's the mean minus 1 standard deviation. So if you go 1 standard deviation to the right, that would be the mean plus 1 standard deviation. And the reason I know it's 1 standard deviation instead of 2 or 3 is because it tells me this number right here. And that's about 68%, which is what the 1 sigma rule says. The 1 sigma rule for the empirical rule. So it's just mu plus 1 standard deviation. All right. A lot of these problems going forward will need tables. Notice that you have lots of table buttons here. Some of them you may have the table button here. Some of them you may have to come here, and if you notice, well, let me go back. This said normal table negative infinity to negative z, negative infinity to z. Those are in here. If you just go to standard normal table, you can pick those. That's the 2 that I use whenever I explain how to do this in any videos and in class. If you go in through your book or the help me solve this or something, it may show you another way, like by using symmetry, but I usually use these 2 tables right here. I found that it makes more sense to students to use those 2. All right. So this says find the area under the standard normal curve to the left of z equals 2.13. All right. The way that our tables work, so let me go to our tables. We use tables A and B. And this is here in your formula sheet. Here's standard normal distribution for A, standard normal distribution for B. A has all of the negative z-score values, B has all the positive z-score values that we use. So the way that our tables work, when we look up something, it will give us the area to the left of that. So if I look up, negative 0.1, and I think that's a 9 column there, negative 1.9, then the area to the left of negative 1.9 is 0.4247. All right. If I come down here and I look up a positive z-score, like let's say I looked up 1.00 right here, 1.00, that would mean that the area to the left would be 0.8413. So the total area is always 1. Okay. So if I need the area to the left, I take the value from the table. If I need the area to the right, since I know that the entire area under the curve is 1, I'll say 1 minus the area that I get from the table. Okay? And that's a very important concept if you're using table A and B. When you look up a z-score, it will give you the area to the left. All right? And this particular problem asks us, find the area of the standard normal curve to the left of z equals 2.13. So we're going to go to our table and go to 2.13. Now, if you use the table that comes with this here, let me show you what you can do. So we know it's a positive z-score, so pick the z that has that's positive. You see that one's negative, this one's positive. So if you click that and we go to 2.1, and we need to make sure we're in the right column for 3. So this is the column for 3. So 2.13. All right, it's right here. And if I select that, it put it in the blank for me. So that's pretty neat that if I select it, you can even, I think, right click and copy if you need to, but know that if you do click a number in the table, it's going to put it in there for you. So less work for me. All right, now this is find the area under standard normal curve between two values. Okay, so let me show you what that would look like if it was between two values. So this is problem number 11. If I'm under the standard normal curve, and this is going to be true for any time I figure out the area between two values. So for our problem that we're working out, it gave us a z of 2.92 and a z of 2.62. So those are pretty big z values. If I had to guess where they are, see, this is almost 3 standard deviations away from the mean, and this is about 2.5, a little bit more than 2.5 standard deviations away from the mean. And remember, the mean, or z equals 0, for a standard normal distribution is right here in the middle. So the one furthest to the right is going to be the bigger number. So one of those is probably about right here. And then, let's see, so we'll put it in that color. And the other one is just a little bit to the left of that. It's not very far to the left of that, about right here. Now, what it's asked me to do is find the area between the two. And we have to do this a lot if we're looking at different values. So I'm trying to find this little bitty piece of the area. And that's a really small piece. It's actually even smaller probably than I've drawn there. So we just have to, if we find the area in the table of the one furthest to the right, or the bigger one. So if we find the area in the table of this one, it's going to give us the area all the way from the left up to that point. And then if I find the area in the table of the one that's to the left of that, it's going to give me the area of all of this up to that point. And so if I take the bigger area and I subtract the smaller area, that'll give me the area that's left between the two. All right, we have to do that a lot whenever we're trying to find probabilities between two values. And these areas correspond to probabilities. Okay, so I need to go to my z-score chart, which I've already done, and I need to look up 2.92. So you might want to do that just to make sure you know how to do that. And the area that I got was 0.9982. And then I went to my z-score chart and I looked up the area for 2.62, and it gave me 0.9956. All right, so I need to take the bigger and subtract the smaller from it. It wouldn't make sense to have a negative area, would it? You can't have a negative area, just like you can't have a negative probability. These areas correspond to probabilities. So whenever I say 0.9982 minus 0.9956, I get 0.0026. So yeah, this area is definitely bigger than 0.0026 units, but it's kind of hard to illustrate whenever the z-values are so close together. .0026. All right, find the value of z. Okay, so this is a different problem. This isn't exactly like what we just did, but it's similar. So we're looking for a z value such that 0.1 of the area lies to the left of z. It says round the answer to 2 decimal places, but z-scores are always rounded to 2 decimal places. Maybe if you do it in a calculator it wouldn't be, but using our tables, all the z-scores will always be 2 decimal places. So we want to find the z value. So we're not looking for an area like we were on the previous problems. We're looking for the z such that 0.1 of the area lies to the left of z. Alright, so I'm going to show you graphically what we're talking about. So here's our normal curve here, standard normal curve. And let's say that this that I have shaded here, let's say that that was 0.1, that area was 0.1. I'm looking for the z value right here that would have an area to the left of 0.1. And I have to do that if I know a probability, but I'm looking for a z that goes with a certain probability. So what I have to do is I go back to my tables, and so I'm going to be on the left side. I'll use this table to show you what I'm talking about though. So all of these are areas inside here, which again, remember, correspond to probabilities. What I need to do is get as close to 0.1 as possible. I don't look up a z-score of 0.1. I'll look up an area and get as close to 0.1 as possible and see which z-score that corresponds to. So if I look at my table, get as close to 0.1 as I possibly can. All right, look at this one right here. 0.1003. So let's check the one on both sides of it. So this is 0.1020. This is 0.0985. This goes out to the tenths, hundredths, thousandths, 10,000ths place. So this one is 15 10,000ths below the answer. This one is 3 10,000ths above the answer. This is 20 10,000ths above the answer. So this is as close as I can get. So I need to see which z-score does that correspond to, and that's my answer. So negative 1.2, and then see what column this is. Negative 1.28. That's the z-score, negative 1.28. Now on this problem, it's the same type of problem, but it says find the z-value such that 0.09 of the area lies to the right of z. The last one was to the left of z. This one is to the right of z. So here's what I'm trying to figure out. Let's say I have my standard normal curve. Alright. And it said it wants to know what is the z-value that would have 0.09 to the right. So what I need to do is imagine that I had a little piece of under the curve like this, and that was 0.09 of the area. So I'm looking for the z-value that would have 0.09 to the right. The problem that we run into here is that that's not the way that our tables are made. The tables always give us the area left to right. So what I need to look up in my table, if I said 1 minus 0.09, that's 0.91. So if I look up all of this area, 0.91, that will give me the z-value that would correspond to an area to the right of 0.09 and to the left of 0.91. The problem doesn't tell us about that. We just have to figure it out. So let's look at the table and let's get as close to 0.09 as we possibly can. I'll use this table this time. Since we're on the right side, it is going to be, and don't click this 0 to z, it is going to be a positive z-score. I know that because anytime you're on the right side of the standard normal curve, your z is positive. Anytime you're on the left side, it's negative. And when I'm talking about sides, I'm talking about from the middle. Alright, so remember, we're looking for as close to 0.91 as we can get. Alright, so here is 0.9099. Now you see that's really close to 0.91. That's 1/10,000th off. Look on both sides, neither one of them. I know this says 0.91, but it has a 1.5 after it. So this is 15/10,000ths too big. This is just 1/10,000th too small. So this z-score, if I click on it, it's going to put that in the blank. So I have to look at the z-score though. 1.3, and then go up in this column. 1.34. That's what I have to put in there. Alright, the diameter of ball bearings are distributed normally. The mean diameter is 80 millimeters and the standard deviation is 3 millimeters. Find the probability that the diameter of a selected bearing is greater than 86 millimeters. So we're going to use the same tables. The thing is, it didn't tell us what z is equal to. So this is where we have to start calculating z, and we need to see if it's a greater than problem or a less than problem. That's the main things that we do. We have to identify what we need. We have to calculate our z with the z-score formula, which is z equals x minus mu over sigma. Alright, so we need to see what all our variables are, calculate z, and then figure out if it's a greater than problem or if it's a less than problem. So on this problem, it tells us the mean diameter, this is the population mean, is 80. It's 80 millimeters. The standard deviation is 3. We want to find the probability that a randomly selected bearing is greater than 86. Okay, so our x in our formula is going to equal 86. Another important part is that it's a greater than problem. When it's a greater than problem, once we figure out our z-score, we want the area to the right if it's a greater than problem. Remember, that's not the way that our tables are made. So what we'll do is we'll get the area to the left, and then we'll say 1 minus that area, and it'll give us the one to the right. Okay? So let's figure out the z-score first. So we have to say 86 minus 80 divided by 3. Well, that is 6 divided by 3. And we always went around this to 2 places because of our z-score chart. That's 2.00. All right, so I'm just going to draw you a little picture of what we're actually finding. So we're going to find an area, and that area is going to correspond to a probability. If I had to guess, I would say 2 standard deviations is probably, or a z-score of 2.00 is probably about right here. So what we want, this is where z would equal 2.00. Since this was a probability talking about greater than, we want the area to the right. So all we have to do is look at our table, and it'll give us the area to the left, and we're going to say 1 minus what it gives us. All right, so let's go to our table. And our z-score was 2.00. So 2.00 is right here. So if we say 1 minus this, that will give us the area to the right. So 0.9772. All right, so 1 minus 0.9772 would be 0.0228. So that's what that area is. That's 0.0228. And that's the probability. So what does that mean? The probability of selecting a bearing and its diameter being greater than 86 millimeters is 0.0228, or about 2.28% chance of that happening. But it wants us to write the answer as a decimal. So 0.0228. And it would help if I pull the test up. All right. The weights of newborn babies born at a local hospital are believed to have a normal distribution with a mean weight of 3,280 grams and a standard deviation of 452 grams. So you need to write down, this is your mean, this is your standard deviation. If a newborn baby at the local hospital is randomly selected, find the probability that the baby will weigh less than 3,686 grams. All right, this is a less than problem too. That's important. So let's write down these values. All right, so we were given the mean weight was 3,280. The standard deviation was 452. And we want to know the probability that our X, or one randomly selected baby, will be less than 3,686 grams. All right, so that's our X value for our formula, 3,686. So Z equals X minus mu over sigma. So that's 3,686 minus, then my mu is 3,280 divided by my standard deviation, 452. All right, if you punch that in your calculator, you're going to get a long decimal. You're going to get like 0.89823. But remember, for z-scores, we always run around to 2 digits. So that's going to be 0.9, then look at the, 0.8, well, actually, if you look at the next digit, that's going to make that a 10. So that is going to be 0.90. All right, since this was a less than problem, what we're actually trying to figure out, let's see, here's our normal curve, one standard deviation, that's almost one standard deviation, 0.9. It's probably going to be a little bit, it's going to be probably about right there. So what we're finding is this area here. Since this is a less than problem, we want the area to the left. That's how this problem is different than the previous problem. I like less than problems because that's the way that our tables are made. So if we just look up a z-score of 0.90, that will be our answer. Okay, so let's go and let's look up a z-score. I'll go to this table here, a 0.90. This is the positive z-score table. So this is the hundredths of 0, so 0.90. So right there, that's our answer. I'm going to click on it, it put it in our blank for us. Alright. Alright, consider the probability that at least 83 of 278 houses will lose power once a year. Choose the best description of the area under the normal curve that will be used to approximate binomial probability. When you approximate binomial probability, this isn't the exact same thing we were doing, and it's not even asking us to find the answer. It just wants to know where would we look to find the answer. Okay, so we have to write down what does at least mean. That's the first thing we need to do. So for problem number 16, we're looking for the probability that x is at least means greater than or equal to 83. That's at least 83. So to do this approximation, we have to use continuity correction. The best table that I found, and I just look up continuity correction table on the internet because your book doesn't have, I didn't see a good table like this. Once we have this written down, if we look and see what we're doing, here we're doing greater than or equal to problem. So if you write down what we're looking for, so if we're doing greater than or equal to, then the x value that we need to use, you have to say the x value, I know it's n right here, but it's n minus 0.5. See, every time you're either adding or subtracting 0.5, but if you do greater than or equal to, it says to subtract 0.5. Alright, so if I subtracted 0.5 from that, that would be 82.5. This is a greater than problem. So with greater than problems, remember you do the area to the right. So the way that we would find our answer will be the area to the right of, it's not really the area to the right of 82.5, it will be the z-score for 82.5. And it didn't ask us to find that. Let's go back and look at our choices. Alright, so the area to the right of 82.5. So it's this first choice here. So that says to the right of 83.5, to the left of 82.5. And the reason why we need to go to the right is because it is a at least, which means greater than or equal to.